Our project is titled Capturing Inauthenticity, the Importance of Context in Fake News Detection. I'm Alex.
I'm Meng.
So why fake news? There are strong indications that false information was weaponized at an unprecedented scale during the 2016 US presidential campaign, with the help of social media giants Facebook and Twitter. Fake news in a political context can be defined as intentionally false published information intended to mislead and influence voters and sway an election or passage of law. With billions of users globally and a large majority of Americans using these platforms, the rate at which fake news can spread is faster than ever. So the dataset we use is called the Liar dataset, which contains 12,000 labeled short statements from PolitiFact.com. We selected this dataset because besides the statements, it contains extra metadata such as the speaker and their party, which can help explore our hypotheses. So we had two hypotheses. Our first was that deep learning architectures can find subtle language patterns based solely on statements to detect inauthenticity without any contextual knowledge base. Our second hypothesis is that jointly modeled statements and contextual metadata will significantly improve the performance of fake news detection. Our approach is depicted in the diagram here. We first take the statement and find an embedding in 100-dimensional space for it. We experimented with learning multiple different embeddings to be discussed later, but they include the use of deep learning models. The metadata includes two types of features that we distinguish between. The contextual features include the topic, speaker, job title, party, and venue, and these categorical features are binarized and converted to a single vector. The historical features include counts of the truth or falsity of past statements. Oddly, there are 6 labels, but only 5 counts provided in the dataset. These 5 counts are normalized to be a valid probability distribution and provide a 5-dimensional feature vector. We concatenate the features from these 3 sources and feed it into a linear classifier, such as logistic regression. We focus on 2 tests. One is 6-way classification, and the other is binary classification, with the essentially true class being green and the essentially false class being red. The most trivial model we have is converting a statement to a vector is sentence to vec. We first consider glove word embeddings trained by deep learning, which give 100-dimensional outputs. To convert a statement to a fixed-length vector, we simply average the 100-dimensional embeddings of each word in the statement. This is definitely not the best way to find a sentence embedding, but it provides a baseline for when we compare other statement embeddings.
Use the fake news dataset. We can train or fine-tune language models to get sentence embeddings from pre-trained word embeddings. In this page, we show 2 architectures where BiOSTM employs the bidirectional recurrent structure to find the correlation among the word embeddings of a single sentence and summarize it into the sentence embedding, while CNN uses convolution operation to process the word embedding matrix of a single sentence. There's another state-of-the-art language model, BERT. It has proven to be a conceptually simple while empirical a powerful model on different natural language processing tasks, including the sequence-level classification problem. Therefore, we can basically fine-tune the pre-trained BERT model using our fake news dataset, then extract the sentence embeddings. We tested different models on the binary classification problem using different features. We can see the logistic regression using only metadata beats all other deep learning models using language statements, which shows that the metadata information is crucial for detecting the fake news. The table on the right also demonstrates the importance of historical counts information for the detection of fake news. It's also worth noting that if only language statement is available, BERT gives it the best F1 accuracy score.
Here's an example where logistic regression with only the metadata was correct, but logistic regression with all features was incorrect. The speaker had a history of 28% true statements and 72% false statements, so we would predict correctly that this was essentially false given only the history. However, if you or I looked at the statement and had to guess, it sounds like it could go either way. In fact, if just given the statement, I would probably believe it were true since the wording is pretty normal and there's nothing outrageous about it. Hence, the sentence feature part may have thought this way too and pulled away the prediction from being false. Thank you for listening.